Embodied AI cannot rely on a single web-scale shortcut like text models do. It requires a structured ecosystem of diverse data sources. While large language models learn to see and speak by consuming the internet, robots must understand physical states, forces, and actions. Because no single dataset provides everything, researchers must combine multiple heterogeneous sources. This paper introduces the Embodied Data Pyramid, a systematic framework designed to organize, compare, and integrate these diverse data streams for training generalist robots. The primary challenge in robot learning is the fundamental tension between data scalability and robot alignment. Highly aligned data, like direct real robot trajectories, is extremely expensive and difficult to scale due to hardware costs and human labor. Conversely, highly scalable data, like web videos, lacks direct action signals and robot-specific physical grounding. Simulation sits in the middle, offering cheap, parallel data generation, but it remains constrained by the sim-to-real gap. Balancing these trade-offs is key to building robust embodied foundation models. The Embodied Data Pyramid organizes all available data into 5 distinct, complementary layers based on their physical grounding and scalability. At the very apex sits real robot data, which is directly executable but highly expensive. Below it is UMI-style data, collected using handheld grippers without a robot in the loop. The middle layer consists of egocentric and exocentric human videos. Below that is simulation data, generated in physics engines. Finally, the base consists of general web-scale vision language data, providing broad semantic priors. Real robot and UMI-style data provide the most direct, physically grounded action supervision for manipulation tasks. Real robot data directly captures the closed-loop relationship between perception and action on target hardware, making it highly accurate but difficult to scale. UMI-style data bypasses the robot by using portable, handheld grippers with cameras and tracking sensors. This allows human operators to collect thousands of diverse, real-world demonstrations in the wild, which are then mathematically retargeted to robot embodiments. Egocentric, simulation, and general data provide the massive scale, diversity, and physical priors needed for generalization. Egocentric videos capture humans performing everyday tasks, offering rich priors on hand-object interaction and task structure. Simulation data allows robots to practice millions of trials safely in parallel, providing exact ground truth labels for contacts and object poses. Finally, general vision language data teaches the model broad semantic concepts, spatial relations, and common sense reasoning before it ever touches a physical object. Reconciling heterogeneous action spaces across different robots requires systematic structural and geometric alignment. Because different robots have different joints and control interfaces, models use structural alignment strategies like semantic action slots to map actions into a unified vector. For spatial actions, geometric alignment is crucial. Models must translate actions into consistent coordinate frames, choosing between robot-centric, camera-centric, or wrist-centric representations to ensure that similar visual motions map to similar numerical actions. Different embodied model paradigms utilize the data pyramid layers in distinct ways to build specific capabilities. Embodied brain models focus on perception and high-level planning, relying heavily on action-free web and egocentric data. Vision language action models, or VLAs, map observations directly to low-level control, requiring action-labeled real robot and simulation data. World action models, or WAMs, learn to predict future video frames and simulate environment dynamics, utilizing both action-free video pre-training and action-conditioned interaction data. Despite rapid progress, current embodied datasets suffer from a lack of standardized tactile feedback and a severe bias towards successful demonstrations. Visual data alone cannot capture contact forces, friction, or slip, which are critical for dexterous manipulation. Furthermore, most datasets discard failures, leaving robots unprepared for real-world errors. Future data collection must systematically preserve failures and annotate them with recovery behaviors, while also standardizing tactile sensor formats to enable contact-rich learning. The Embodied Data Pyramid provides a unified roadmap for designing next-generation, generalist robotic systems. By moving away from single-source training and systematically combining real robot, UMI, egocentric, simulated, and general web data, we can build models that possess both high-level cognitive reasoning and precise low-level physical control. This data-centric perspective shifts the focus from merely increasing dataset size to improving informational coverage, acquisition efficiency, and cross-embodiment alignment.